Coulomb's law is a quantitative statement about the force between the point charges. When the linear size of the charged bodies are much smaller than the distance separating in between them, then the sizes may be ignored and the charged bodies are treated as nothing but point charges as stated before. Coulomb measured the forces between 2 point charges and found it varied inversely to the square of the distance between the charges and directly proportional to the product of the magnitude of the two charges and acted along the line joining the two forces. Thus, if 2 point charges q1 and q2 are separated by a distance r in vacuum, then F is equal to k mod of q1 q2 by r square. R is the distance, k is a constant, q1 and q2 are the charges. Okay, how did Coulomb arrive at this particular law from his experiment? He used a Taurasian balance. What is it? It is basically used for measuring forces between two charged metallic spheres. Okay, see, when the separation between the two spheres is much smaller than the radius of each sphere, the charge sphere may be regarded as point charges. However, the charges on the sphere were unknown to begin with. How could he discover such a relation? Coulomb thought that in following simple way. Suppose the charge on the metallic sphere is q. If the sphere is put in contact with an identical uncharged sphere, the charge is spread over the two spheres, so it will be obviously q by 2. By symmetry, the charge in each sphere will be q by 2. Repeating the process, we can get q by 2, q by 4, etc. Coulomb varied the distance for a fixed pair of charges and measured the force of separation for different separations. He then varied the charges in pair, keeping the distance fixed. So first he varied force, then he varied the distance next. Okay, keeping the force constant or and the distance constant in respective cases. Coulomb's law, a simple mathematical statement, was initially experimental, right? In this manner described above. Okay, so r here is almost 10 to the power minus 10 meter in subatomic level. K is nothing but 9 into 10 to the power 9 Newton meter square Coulomb square inverse. Okay, is nothing but 9 into 10 to the power 9 Newton meter square by Coulomb square. Okay, so force here can be written as 9 into 10 power 9 if q1, q2 and r is equals to 1. Thus, if we can say that if 1 coulomb of charge is placed at a distance of 1 meter from another charge of the same magnitude in vacuum, experience an electrical force of repulsion of magnitude 9 into 10 to the power 9. 1 coulomb is evidently too big a unit to be used, so we can use 1 millicoulomb, which is 10 to the power minus 3 coulomb, or 1 microcoulomb, which is 10 to the power minus 6 coulomb. K can be written as also 1 by 4 epsilon naught. Epsilon naught is nothing but the permittivity of free space, which is 8.85 into 10 to the power minus 12 coulomb square Newton inverse meter square inverse. A Taurasian balance is nothing but we have K, which is equals to 1 by 4 epsilon naught. Epsilon naught is 8.854 into 10 to the power minus 12 coulomb square Newton inverse meter square inverse. Since force is vector, it is better to write Coulomb's law in vector notation. Let the position vectors of charges q1 and q2 be r1 and r2. So force on 2 due to 1 is 1 by 4 pi epsilon naught q1 into q2 by r2 due to 1 whole square into r2 due to 1 r cap 2 due to 1. Simple. So if you write r cap 2 due to 1, it is r cap 2 due to 1, which is equals to r21 by r21 unit vectors. Okay, so r12 is nothing but r21 minus r12. Since we see that force 2 due to 1 is k q1 q2 by r2 due to 1 square. Equation is valid for any sign q1 and q2, whether positive or negative. If q1 and q2 are of the same sign, either both positive or negative, f21 is along r21, which denotes repulsion and should be for like charges, and opposite, which denotes attraction. Okay, so f12 is minus of f21. Coulomb law agrees with the Newton's third law. The forces between the two charges q1 and q2 are in vacuum. The example 1.3, Coulomb's law for electrostatics between 2 point charges and Newton's law for gravitational force between two stationary point masses both have inverse square dependence on the distance between the charges and masses. Compare the strength of these forces by determining the ratio. So basically we have to take out Fe by F3. So electrostatic, which is K q by r square, simply we can write it as minus k e square by r square, and Fg, which is minus g mass of proton into mass of electron by r square. So we get the answer on solving. Next we have on finding the estimates of acceleration. Acceleration is nothing but force by the masses. Okay, next example 1.4, we have a nylon thread which is charged metallic sphere A suspended by nylon thread. Another charged metallic sphere B by an insulating handle is brought close to A such that the distance between the centers is 10 cm. As shown in figure 1.4, the resulting repulsion of A is noted, and spheres A and B are touched and C is removed. So when two spheres are touched, the charges get distributed. Yeah, sorry for the inconvenience. Okay, so let's continue. So basically next questions we have, that was example 1.4. When two spheres are touched, the charges get distributed, which will become q by 2. So q by 2 plus q, which is q by 2 plus q by 2, which is 2q by 2q plus q by 2 by 2. So 3q by 2 into 2, which is around this much. Okay, so this is the magnitude of the particular charges. So your charges remains unaltered. Next comes forces between multiple charges. It is the vector sum of all the forces on the charges due to the other charges. This is the principle of superposition. F12, as I already told you, F21. So see, this is the diagram. We can see here that we have R2, R1 and R3. So this is R1 due to 2, R1 due to 3. This is F13, F1 straight, F12. Similarly, here there is multiple charges. The system of 3 charges. There is multiple. Here there is multiple charges. Okay, so we have force 1, q1, q2, q3. So q4 goes f41, f21, q2, f31, q3, q3 either. And f5 like this. Okay, next. So we can calculate each. So f1 is nothing but f12 plus f13 plus f14 and so on. Okay, basically it is just the addition, the parallelogram of addition of the vectors. Okay, next we have a question. Because the question states that there is 3 charges q1, q2 and q3, each which is equal to q at that vertices of an equilateral triangle of side L. What is the force on the charge q placed at the centroid of the triangle as shown? So basically it's the centroid of an equilateral triangle. It divides in ratio 2:1. So this is 2, the down portion is 1. Okay, so sine 60 degree. The above part can be written as AP by C. Sorry, AP by L. This is L. This is L. Okay, so this upper part cos 30 degree, which is AP by L, root 3 by 2, which is AP by L. So basically we calculate it. Next we have question 1.6 example, which is the same. Okay, next we have electric field. So what is electric field? Electric field is basically force, is, as I already told you, q1 q2 by r square. So force is equal to charge into electric field. Okay, Electric field due to charge q at a point in space may be defined as the force. That force which is of a unit positive charge experienced, it would experience its place at that point. So electric field is nothing but force by charge. So if we take for a negligible small amount, that E is equal to limit q tends to 0 force by q. It is the region of the charge body in which another charge body experiences electrostatic force. The charge q which is produced electric field is called the source charge. The charge q which tests the effect of a source charge is called the test charge. Fr is equal to q e r. This field exists in 3D space. For every positive charge, it would be directed radially outwards, and negative charge, it would point radially inwards. Okay, the distance r is basically the total distance between the two charges, and magnitude is due to the point charge same on the sphere. Okay, next we have electric field due to a system of charges. What is it? It is nothing but we keep on adding it. Okay, so E1 E plus E2, it is with respect to r distance. Okay, so E1 r plus E2 r. Next we have the physical significance of electric field. The term field in physics generally refers to a quantity that defined at every point in space and may vary from point to point. It is a vector quantity, but force is a vector quantity also. Okay, the field picture in this, the accelerated motion of a charge, supposing q1 produces em waves which propagates with the speed reach q2 and causes a force on q2. So they have an independent dynamics of their own. Electric field intensity, electrostatics force per unit charge is unit is Newton per Coulomb. Similarly, a simple example is given in which there is nothing but there is only to find the find the acceleration. Okay, then we have also example 1.8. Then we have 1.8 electric field lines, which is also a vector quantity. Properties of electric field lines are that no two field lines ever intersect each other. Field lines are always perpendicular to each other, and to the conductor, no field lines are directly proportional. Number of field lines, no field lines ever intersect each other. Field lines are always perpendicular to the conductor and start from positive end at negative. They can be taken as continuous in charge-free region and do not form closed loop. Uniform and non-uniform electric fields are there. They exert lateral pressure during repulsion between like charges, contract longitudinally during attraction between unlike charges. Number of field lines is directly proportional to amount of charge. Flux, electric flux is nothing but E into A. Okay, so flux is what? Flux is basically the delta phi E dot delta S. Electric flux can be written as ED cos theta, and its unit is Newton Coulomb inverse meter square. Okay, electric dipole. Next topic we have the field of an electric dipole. So we have different positions. We have the field of an electric dipole with 4 points on axis, so points on equatorial plane. For axis, we have E is equal to K Q A by R cube. On equatorial plane, we have KQ by R square plus A square. Okay, next we have physical significance of dipoles, that is the dipole moment is 0. Okay, next we have dipole in uniform external field. Magnitude of torque is QE sin theta, 2QEA sin theta, tau is P cross E. Continuous charge distribution, so it can be written as surface charge density, which is delta Q by delta L, linear charge density delta Q by delta L, and volume charge density delta Q by delta V. For surface charge, we have the unit Coulomb per meter square. Linear charge, we have Coulomb per meter, and volume we obviously have Coulomb per meter cube. So delta can be written as K P delta V by R square. Okay, Gauss law. What is Gauss law? So these are the linear charge surface charge diagrams. Okay, next we have Gauss law. Before Gauss law, let's see what's continuous charge distribution. As I already told you, that extremely close space charges from continuous charge distribution. Gauss law, delta phi is E dot ds, which is KQ by R square into R cap into delta S, which is KQ by R square into delta S. Then we have applications of Gauss law. What are the applications of Gauss law? In infinitely long straight uniformly charged wire, E is equals to lambda by 2 pi epsilon naught R, where lambda is nothing but the surface charge density. Okay, then we have fields due to uniformly charged infinite plane sheet, which is E is equals to sigma by 2 epsilon naught, and uniformly charged in spherical cell, which is E is equal to KQ by R square R cap. Okay, so this is how we end the chapter. This is the summary.